The last few confidence intervals we came up with, we were working with a population standard deviation, but more often than not, if you don't know what the mean is, then you don't know the population standard deviation either. And so it would be good if there was another way of finding these confidence intervals that didn't rely on the population standard deviation. And there is, and there's actually an interesting story that goes behind this, which is about 150 years ago, there was a guy that worked for the Guinness Brewing Company, and his job was to come up with more efficient ways of brewing beer. And of course, he couldn't figure out the information for the entire population. Otherwise, well, he'd have to drink all the beer that was produced by the company, and he couldn't do that. So he had to come up with some other statistical method, and he did. But the brewing company that he worked for, which actually was Guinness, wouldn't allow him to publish the research that he did while he was working for them. So he thought it was so important that he published it under the name student. So when you see the term studentized t-scores, that's what it is. William Gossett was the guy's name, and he published it as a studentized version of X bar. So X bar is the sample mean, and S down the bottom here is the sample standard deviation. And what this brings to us is that instead of using z-scores, we're going to be introduced to a whole new set of scores called t-scores. And t-scores and t-curves work in some ways very similarly to what z-scores do, but they are a little bit different. Okay, and the other thing that's important to remember is when to use which one. You use z-scores when you know the population standard deviation. You use t-scores when you calculate that standard deviation only from the sample and not from the entire population. So let's take a look at what these t-scores look like and where to find them. Well, the other thing that you're going to notice is that in order to use these t-scores, you're going to need to know your sample size. And the sample size subtracted by 1 gives you what we call the degrees of freedom. All right, so when you scroll through your formula card, right, if you go all the way to the top and you're scrolling through, here's chapters 4, 7, 9, 10. You've got your z-score table. Underneath it is your t-score table, and there's a little t-alpha. So t-alpha is the area that's to the right of that z-score, right? So it's that t-score having an area of alpha to the right of whatever that is, right? A little bit different from the z-score table. Z-score tables are to the left. T-score tables are to the right. All right, the degrees of freedom go down the side, so you've got 1 through 49 on the first page, 50 all the way up through 75, and then it goes up by fives, by hundreds, and then by thousands. Once you get to the real high values for degrees of freedom, they start to get very close together, right? So that's why they jump up by hundreds. You notice the numbers here don't change very much. And once you get to about 1,000 or 2,000, then T-scores and Z-scores basically become the same. The other thing is you're limited to your alpha values. So you have T where alpha is 0.1, alpha is 0.05, 0.025, 0.01, 0.005, and that's about it. Your graphing calculator, if you have one, will actually give you more accurate values if you wanted an alpha level of like 0.03 or 0.037 or something like that. You could actually use your graphing calculator to come up with numbers that are that accurate, or StatCrunch that comes with the MyMathLab program probably does that too. All right, so that's where you find your T-alpha scores. All right, what else is interesting? Let's try a couple of these just to look at the table and see what we come up with. So suppose I want to find T of 0.01 with 17 degrees of freedom. So I want to find the T-score that has an area of 0.01 to the right of it with 17 degrees of freedom. Okay, so T of 0.01 is right here, 17 degrees of freedom. There it is. If I can highlight it, 2.567. Right, so 17 degrees of freedom, T-score with alpha equal to 0.01. There you go. All right, so pretty far up, to a little over 2.5 standard deviations above the mean. All right, 17 degrees of freedom, by the way, means that your sample is 18. So the degrees of freedom is always one less than the number in the sample. All right, so the first question up here, a couple little examples, says find for a t-curve with 8 degrees of freedom, find the t-value having an area of 0.05 to the right. So remember, when we do these, that alpha is our subscript. So we're looking for 0.05, that's t of 0.05, with 8 degrees of freedom. Here we are, 1.86. Right, so there's alpha equals 0.05, 8 degrees of freedom. All right, let's take a look at C. C says the t-value having an area of 0.01 to the left. Well, 0.01 to the left is way down here. But because the curve is symmetric, why not come over to the top over here and find the spot where the area is 0.01 to the right, and then just tack on a negative. So what do we have? 8 degrees of freedom, and we want t of 0.01. T of 0.01, 8 degrees of freedom. Here we are, 2.896. But that 2.896 is up here. We want it down the other side, so let's make it negative 2.896. All right, and then the last one says the two t-values that divide the area under the curve into a middle area of 0.95, right? So the t-curve for large enough values begins to look much like the normal curve. And then the outside areas are 0.025 over here, 0.025 over here. So I'll use the same trick as before. If I can find t.025 with 8 degrees of freedom, that'll give me the number up on the top, and then the other one is just the negative version of it. All right, so let's go back to our t-table. T of 0.025. So it's the one in the middle here. 8 degrees of freedom, 2.306. All right, so I got a 2.306 on the top, but then I also have a 2.306 on the bottom, and that will create an area of 95% in the middle, and then 2.5% essentially on either side. All right, so let's take a look at the one mean t-interval procedure. Not a nice t-interval procedure. This is one mean interval procedure. So the first thing is you need to figure out the alpha from your confidence level. So for a confidence level of 1 minus alpha, you're going to find t alpha over 2. Okay? Find your degrees of freedom by subtracting 1 from the sample size. If the problem's nice, they'll give you the sample standard deviation. If they're not, then you're going to have to calculate that standard deviation for the sample. So a reminder of what that formula is also on your formula card. You could zip up to Chapter 3 and find the way to calculate that standard deviation for the sample. Remember, for the sample, you divide by n minus 1. And then the confidence interval is very similar to the one we use for z-scores. You're going to go from the mean below a little bit and above. The only difference is instead of using z-scores, you're using t-scores. And instead of the population standard deviation, you're doing the standard deviation just for that sample that you found. All right, so let's try a couple of these and see if it makes sense. This one's about commute times in Washington, D.C. So I'm going to sample 30 commuters in Washington, D.C. This tells me how many minutes it took them to get to work. I want to find a 90% confidence interval for the mean commute times of all commuters in Washington, D.C. Now, notice that I don't have information about the population standard deviation. So in this case, I'm going to have to use the information only from my sample. Okay, so because I'm using information only from the sample, I know I'm going to use t-scores instead of z-scores. Now, it tells me here that the sample mean is 27.97 minutes. Sample standard deviation is 10.04. So that does save me some time, right? It lets me figure out right away sample mean, sample standard deviation. If it didn't give you that, you would have to do the calculations on your own. All right, so the sample mean was 27.97. Sample standard deviation was given as 10.04. There were 30 items in the sample. It wanted a 90% confidence interval, so 90% confidence level means my alpha is 0.10, right? 1 minus 0.9 gives me 0.1. So I'm looking at t of 0.05, right, because that's t alpha over 2 for 29 degrees of freedom. All right, let's figure out what that number is from our t chart. So t of 0.05 for 29 degrees of freedom gives me 1.699. Right? 29 degrees of freedom, T of 0.05, 1.699. Right, what does the procedure tell me to do? It says to take the mean, which is 27.97, plus or minus that T alpha over 2 value, so 1.699, times the sample standard deviation over the square root of n. And then the rest is just calculations. So take 10.04, divide it by the square root of 30, and multiply it by 1.699. All right, so this gives me 27.97 plus minus. The number that I get is 3.114. So let's make that 3.11 to be consistent with the accuracy that we have from the minutes. All right, so let's do a plus and a minus. So let's do 27.97 subtract 3.11. That gives me 24.86. And then the other version is to go back to what I typed and replace that minus with a plus. 31.08. All right, so I'm 90% confident that the actual mean of everybody's commute time in Washington, D.C. falls between these two values, between about 29 minutes and 31 minutes. All right, and I did that using t-scores because I only had the standard deviation for the sample and not for the whole population. All right, let's try another one. Let's try cost of attending an amusement park. So I'm going to sample 25 families, and notice that the data wasn't given to me, but I have enough information from what's written in here to solve the problem. Random sample of 25 families found that the sample mean is $193.32 to attend an amusement park. Sample standard deviation is 2673. I sampled 25 families. And my confidence interval is I want 95% confidence level, so that means my alpha is 0.05. All right, so the first thing is to use that information to find that t value. Once you have the t value, then we throw it into that formula. So my t alpha over 2 is going to be half of 0.05 is 0.025. So I want t alpha over 2 for 24 degrees of freedom. All right, so T of 0.025 for 24 degrees of freedom. Comes down here. 2.064. All right, so now I'll come down here and I'll set up my equation. So I have the mean, which is 193.32. Plus or minus that T alpha over 2, which is 2.064, times the sample standard deviation, which is 26.73, over square root of 25. Yeah, I know that's 5, but I'm just writing that to be consistent. So 26.73 divided by 5. Take that number and multiply it by 2.064. And I get 11.034. So let's make this 11.03. Okay. Again, this doesn't have to be any more accurate than the first one. So if the first one is rounded to the nearest cent, that can be as well. All right, so 193.32 minus 11.03, and I get 182.29. Right, if I go up there and I change the minus to a plus, I get 193.32 plus 11.03, 204.35. All right, so I am 95% confident that based on the sample that I have of 25 families, that the actual cost, the mean cost of attending an amusement park for those families is between $182.29, and $204.35. And that's T-scores. That's how you find confidence intervals using T-scores.